All right, as you can see now, I'm in the classroom with a very big whiteboard. This is for section 7.2b, Gravitational Fields, work number 1, A, B, C, number 2, and number 4A. Now, let me check how this will work. So, for the calculation, you've already seen these two equations before, for gravity and for weight. And I showed you how you can do this. You can find your weight with the gravity equation. If I put in M1 is the mass of the Earth, M2 is your mass in kilograms, and R radius would be how far it is the radius of the Earth from the center of the Earth to you. If you put that in, you'll be able to calculate your weight in newtons. Well, if you put in here M, your mass in kilograms, and A 9.81, you'll also get the same number that you got there. Pretty much the same number in newtons. It might be slightly different methods for sig figs and stuff. And also because the radius is not perfect, for the Earth. Not a perfect sphere. All right. Well, anyway, there's an equation. If you combine them, you can take, this is one equation that can be used to calculate what they call the gravitational field of the Earth. And I'm going to talk about what that means in a minute. But there's another one that we're going to use that's a little bit more, we're not really going to use them very much, but this is one of them. The acceleration due to gravity is equal to, oh no, this is only for Earth. Or as long as you know what G is. 9.81 goes in there, the radius of the Earth, and how far you are from the center of the Earth, squared. And the farther you get, like when you get farther away, that changes your, that changes the gravity acceleration. 7.2c I'll talk about in class, but if you go to the next part, there's a scientist, and I like to talk about him because he's big in chemistry as well, is Michael Faraday. Did many things for chemistry. He also created the first electric generator. Pretty amazing. Amazing scientist. Incredible. And anyway, his theory on what's called on electric fields is what is used to describe gravitational fields. I know that I mentioned to you earlier in an earlier lesson that this equation to calculate gravity, I mentioned that there's also a force of energy of attraction between any two charged particles. Q is the charge of one particle, Q is 2, the charge of another particle, and that's the R, the radius of them. And isn't it interesting that what they call electric fields have electric, like a positive one particle has an electric field around it. A negative one particle has an electric field around it. Just like gravity, the theory is that an object has a gravitational field around it. If an object enters the gravity field, then it will be attracted to it. If an object enters a positive charged field, like if a positive, just say you have a charged field around a positive particle. If a positive particle enters that, well then there'll be a repulsive charge. And the closer you get, the greater the repulsion. If a negative charge enters, well then it attracts. And of course the closer you get, the more it attracts. So anyway, Faraday came up with this idea of gravitational field, or it was applied to gravitational field, and there's a little diagram here that shows you as you get closer to an object. Notice how the arrows on the outside are small, the vector arrows, but as you get closer, they get longer and longer. So the closer you get, the greater the force is pulling you towards the center of the Earth. If you go, far outside, like in outer space, away from all gravity field, well, the Earth, then there's no effect at all. You have zero weight. But then the closer you get, you have a small weight here, larger as you get closer and closer. I've mentioned that to you. Well, there's an equation for this, that a gravitational field is equal to, at any point, what is the gravitational field? So someone just decided to make it a little more convenient equation. And the cool thing is, it will work for any planet, any moon, anywhere you go, as long as you know to find the gravitational field on that planet, you need to know the constant, which we always know, 6.6710 to the negative 11, the mass of the central body, and then the radius, how far you are from the central body. Okay, so the first thing I'll do here, right below that equation, and it gives you some data: the mass of the Earth, Sun, and Moon, and the radius of the Earth, Sun, and Moon. And letter A says, what is the gravitational field of Earth at the Earth's surface? Letter A. Number 1. At the surface of the Earth, what is the gravitational field? Now, we know that when you're on the Earth's surface, we say 9.81. That's the acceleration due to gravity. And by the way, I wanted to show you, well, I'll get to that in a minute. I'll show you in a second how this works. Okay, so 9.81, what we imagine it to be. But let's calculate it this way. So G equals 6.67, 10 to the negative 11, that's your constant, times the mass of the central body. We said on Earth. So on Earth, the mass is the mass of Earth is 5.97 10 to the 24th kilograms. And the radius, if you're standing on Earth, how far are you from the center? We've done that before too. In meters, it will be the radius of the Earth, 6.38 10 to the third. Well, 10 to the third kilometer, but then we got to make it 10 to the 6 meters. I should have just gone on and given it to you in meters anyway. But 10 to the 6 meters. Now, that number on the bottom has to be squared. It seems like we always put r squared there. They combined other equations to get this equation. Okay, so let me just calculate this. So 6.67 10 to the negative 11 times 5.97 exponential 24 divided by 6.38 10 to the 6 twice 6.38 10 to the 6. And I get 9.78. Now, the units of this, and I didn't really show you, didn't do a good job without that, because you know that this is going to be meter squared over kilogram. That's going to be meter squared over kg newtons. Meter squared newtons over kilogram. That's the unit for the gravity constant. You probably do want to write them in if you want to understand this. So meter squared and meter squared are going to cancel. Kilogram and kilogram are going to cancel, but you're left with newtons. And something is not, there's some unit that I don't have. I should have, well, it's newtons. Okay. It should be Newton per meter squared. I guess you can't get it on this. Oh, wait, there's Newton meter squared, kilogram squared. Newton meter squared. Oh, kilogram squared. Sorry, that makes a little more sense. Okay. Newton meter squared over kilogram squared. All right. So this makes sense now. Kilogram is squared, so only 1 kilogram cancels out, so it's Newton per kilogram. Now what it tells us is interesting because the answer 9.79 newtons per kilogram. It means every kilogram is pulled or accelerated or pulled with a force of 9.78 newtons. Now we know that Newton and kilogram can be turned into meter per second squared. I won't go through the math of that, but taking out the units, you can turn it into that. So that's pretty interesting because remember, Newton comes from mass. Well, if you wanted to do it, a Newton is kilogram. MA is a Newton. Mass times meter per second squared over kilogram here. So Newton, if I turn Newton into kilogram meter per second squared, and I keep my kilogram on the bottom, kilograms go away and you have meter per second squared. So all you need to know is that when you have gravity, field is 9.78 Newton per kilogram, that means your acceleration of gravity is 9.78 meter per second squared. Now, it's not 9.81 when you use this information. That's because the Earth is not a perfect sphere. And remember, it's not just the how far from the center, but also where in the latitude of the Earth that you are. So 9.81 is an average, probably of everywhere on Earth that, well, everywhere it's been measured around Earth. So anyway, it's interesting. Maybe places that where people like land is. I don't even know if they did acceleration of gravity above all the water. If that's as much, I'm not sure. I'm not sure why the number is not exactly the same, but pretty close. 9.8, pretty close to 9.8. 9.81 would be the correct value. Again, that is only the average radius of the Earth there. All right. So to calculate gravitational field, if I know the mass of the planet, then I got to know how far are you from the planet. All I put in was the mass of the planet and then how far in meters I am from the center. It will work if I put the mass of the moon, how far from the moon, or the mass of the sun, and how far you are from the sun. You can put that in the same way. All right. So 9.78. But let's talk about what you can do with that number. And I think it's on the next part. It says, number 2, what would it be at 400 kilometers above the Earth's surface? Well, if I wanted to do that, I could just throw that in real quick. 400 kilometer would be 400,000 meters above the Earth's surface. So that would be 400,000 plus what we just had. What do we have right there? The Earth's radius was 6.38 10 to the 6 meters, right? Plus 4 times 10 to the 6 meters. So that would be 400,000 above the Earth. I have to take all that. I have to square all of that. So that's going to be 6.38 10 to the 6, 4 10 to the 6. So that's going to be 1.04 times 10 to the 1, 2, 3, 4, 5, 6, 7. And I have to square it. So I would add those two numbers together. This is the height above the Earth. That's the radius. So from the center of the Earth, first you got to get to the surface. That's from the center of the surface. That's above the surface, 400 kilometers, 400,000 meters. And that would give it to you. So obviously, if that number on the bottom gets higher, then if R gets higher, then the gravitational field is going to get smaller. That should make sense. So let's just see what that's going to be. 6.67 10 to the negative 11 times 5.97 10 to the 24th divided by 1.04 10 to the 7th and divided again 1.04 10 to the 7th. It's going to be 3.68. So it's going to be much smaller than that 9.79 that we saw. 3.68 meters per second squared, or 3.68 newtons per kilogram. So it's strange. So gravitational field, the appropriate unit is 3.68 newton per kilogram. But if you want acceleration of gravity, it's 3.68 meter per second squared. They're the same thing, just different names. Gravitational field or the acceleration of gravity. All right. Number 3 says, what would be the weight in newtons of a 150 kilogram satellite at 400 kilometers above the Earth? So for number 3, and by the way, that was number 2. It became number 2 when I put that number in. 3, above the Earth, what would the weight be? Well, F equals mg. The weight of the satellite will be the mass. It says 150 kilogram, just like we did back in the earlier chapter. And now for 400 kilograms above the Earth, it will be 3.68 will be the acceleration of gravity. And so 552 newtons. Okay, 552 newtons. So just to give you an idea, it would weigh 124 pounds. Okay, if it were 400, that satellite is that high above the Earth, it weighs 124 pounds. However, if the same satellite were on the Earth, and you brought it down here, it would weigh, oh my goodness, 1,500 pounds. That's, close to being a ton, right? A ton is 2,000 pounds. 1,400 pounds. But up at that height above the Earth, where gravity is only 3.68 and not 9.81, then it would only weigh about 124 pounds. There are some people, some weightlifters that could lift that, okay? Could lift that satellite up there. But down here, they could not lift it if it was 1,500 on Earth. Couldn't do it on the surface, but they could do it out there. Just kind of a neat little goofy thing. I just threw that in. Okay, now number 4 says, imagine that the 125 kilogram satellite is released from a shuttle while the shuttle is at rest. Now, at rest would mean, what does that mean? At rest. then we're not going to think about the velocity of the shuttle, but it would be at rest with regard to the rotation of the Earth. I guess to say it's in orbit around the Earth, but perfectly moving with the Earth. Okay, if you release that satellite as it falls towards the Earth, will its initial rate? What will the initial rate of the satellite be? The initial rate at that point will be the same number I showed you, 3.68 meter per second squared. So at that point, I just asked that question so that you know gravity field and acceleration of gravity are the same thing, except one is in field is in newtons. This means newtons acts on every kilogram, and that will be here meters per second squared. You could say that on Earth, G is 9.81 meter per second squared. That's the acceleration. You could also say it's the gravity, that 9.81 newtons of force pull on every kilogram of your mass. Okay. All right. I think there's one more thing, and this is kind of a strange one. Okay. And am I still going to use the 150? Well, I don't know. Well, we'll see. We'll see what we're going to use here. It says, a helicopter is stationary in the air high above a skyscraper. An 11 kilogram box of chocolate weighs 107.7 newtons at this height. Okay, the helicopter's at rest above a skyscraper. I don't know if I need to draw that or not. I mean, a building, a little helicopter. There's my little helicopter. I don't know if that's helicopterish. Okay. Chocolate weighs 107.7. What's the gravity of the field at that location? Oh, okay. All you're going to have to do, so another way to find gravitational field, just think about the units. It's Newton per kilogram, meter per second squared. So if I know that chocolate weighs 11 kilograms, I'm sorry, if I know that the chocolate has a mass of 11 kilograms, put the kilograms on the bottom and put newtons on the top, and it weighs 107.7 newtons, then I can calculate gravity right there. 107.7 divided by 11, it's 9.79. Hey, so not 9.81, but a little bit lower than that. Again, 9.79 would be the acceleration of gravity, or the gravitational field at that location. So what's interesting is you could take that, let's think about this for a minute. If I know the gravitational field, this is just a side note, you don't have to do it. The helicopter could say, well, if that's gravity, 9.79, and I know I know gravity constant, 6.617 to the negative 11, I'd need to know the mass of the Earth below it, and I'd be able to find how high I am from the center of the Earth. Well, yeah, I'd find the radius from the center of the Earth and subtract. I could find the height. I mean, a computer could do it faster, but you could find your height just based on that. So if you're in an airplane or a helicopter or whatever, and you were to say, hey, I know that this can weighs 1 kilogram, and I'm going to put it on a scale, okay? And it weighs 150 newtons. Okay, so 150 newtons is one. Well, it won't be that much. Okay, but then it weighs 8 newtons. Just say it weighs 8 newtons, and the mass is 1 kilogram. So 8 newtons divided by 1 kilogram. That would tell you the acceleration of gravity at that point. But you could also use that equation and find out how high you are above the Earth's surface if you subtract the radius of the Earth from that number that you get. You can find the radius, distance to the center, and then subtract that. Okay, well, just do those problems that I told you. And this is the last math equation. There's some really neat theories in there about, I told you a little bit about Faraday's theory, and I'll talk about it in class, but I want to talk about Einstein's theory and a few other things. But we've done the bulk of the stuff here in this chapter then of the math. So thanks so much, and I will see you guys later.